combination. So we see certain things from Sentinel 4 and we see other things from the other instruments, so there are synergies between these products, and aerosols, which are little particles in the atmosphere, which are very important for air pollution. And the Sentinel 4 instrument will look in this area all the time. So this is another thing where we can combine high resolution imagery together with the infrared. So the red color gives you the temperature. So the more red it is, the colder the air is in the upper troposphere. So this is also a new application which is possible, which we didn't have before. So and then we have one instrument which is very new. Everybody's very excited for that. It's a lightning imager, so it looks at lightning stroke on top of the clouds. So what is really happening, if you have a thunderstorm, before you have hits of lightning to the ground, you have intercloud lightning, which you don't see from the ground. And the intercloud lightning, lightning between the clouds, happens 10 minutes, usually roughly 10 minutes, before you have lightning hits to the ground. So you can increase your warning time, which is quite important. It's a new instrument. We still have to learn a lot of that, and which we will fly also on our geospatial satellite. This is a little bit complicated to explain. So if you have clouds, you have a lot of water vapor into the clouds. You can see that. You look out of the window, you see the clouds up there, which is basically water in the water particle, bigger water droplets in the clouds. But if you have a clear sky, you don't know how much humidity is in there. So, but with a spectrometer, you can really say how much humidity is in this clear sky. And this humidity later will evolve into a cloud. And with the spectrometer, the IRC infrared spectrometer, which we fly a similar instrument on EPS, you can really depict temperature and humidity in clear air. And you can make a 3 or 4D VAR profile of the atmosphere, and this humidity, which is not visible for us, for your eyes, develop into clouds later. And that also gives you a better prediction of developing systems in the atmosphere. On the right side, what we call AMVs, is atmospheric motion vectors. So until now, it is not possible to measure wind in the atmosphere direct. We only can do it indirectly. And what we are doing, we are looking at a cloud, pick a point of the cloud, and see how it moves within the next 5 minutes. And then you have a vector, and you can depict out of that how fast the cloud moves, which is proportional to the wind. That's what we call atmospheric motion vectors. It's the indirect measurement of the wind. And you can do that also with the IRS in clear air. So you can really see the different layers of the air, how it moves in clear air. That is also a new application. Briefly, EPS second generation. As I said, we are putting instruments on 2 satellites. Basically, it's a broad overview what we have. First of all, we have again an infrared spectrometer, which does the same thing from low Earth orbit, which I just explained before. We have a microwave sounder. The microwave sounder is working in the gigahertz area, up to 160 gigahertz, and it really penetrates the clouds. So you see different liquid content in different levels of the clouds. Then we have again atmospheric composition instrument from GMES, which look at CO2, SO2, Stickstoffdioxid, water vapor, CO2, carbon monoxide, and so on. And yes. Then, very importantly, radio occultation. That's basically we're using the GPS signal to depict temperature and humidity of an atmospheric profile. So what is really happening? On the right side, you see the satellite with the GPS receiver. On the left side, you have the global positioning satellites. And when they send out their message, which you also use in your navigation systems, it goes through the atmosphere. The atmosphere bends this line. It's called the bending angle. And the bending angle is proportional to the temperature and humidity within this area. So you can really, when it goes down through the atmosphere, you get a profile of temperature and humidity in that area. And the interesting thing that these measurements are bias-free. Other instruments you have to calibrate, these measurements don't have a bias. So it's called radio occultation, which since 10 years is very important and used on several satellites. Most of the satellites have it already now, and you are using that. So, and then on the then we have also an imager on the EPS second generation first satellite with 20 channels, horizontal resolution 500 meters. A special instrument called 3MI, which looks at aerosols, and which there was a French mission called Polder, where we take benefit of. So aerosols are getting very important for air pollution predictions. And we again have a scatterometer, which I explained before, which looks at wind over the ocean. It measures the reflectance from the ocean, but it can also measure the reflectance. These frequencies. It's a C-band radar, 5.5 gigahertz. It also over land penetrates the soil, and the reflection is proportional to the salinity and the soil moisture. So we can predict also out of that soil moisture, which is quite important for agricultural applications, that you know how much moisture is in the soil. But the penetration is not very, very deep, so only on the surface. To go deeper in the soil, you have to have long wave lengths. And then we have what we call a microwave imager, which goes up to 600 gigahertz, and an ICI instrument which looks at ice cloud phases, so the cirrus. It's a very new instrument who is dedicated to cirrus detections, with cirrus clouds which you see, which are very high. So this is also quite a new instrument. And support to Copernicus. You probably know that this year the EU Council agreed to add the Copernicus program to the next financial 5 years of 3.7 billion. There's regulation in place, and our cooperation with the Commission is basically that we operate the Sentinel-3 mission, the ocean mission, Sentinel-4 and 5 on the GEO and LEO satellites, and the continuation of the high precision ocean altimetry, where we look at sea level range. Yeah, and this really shows then the optional programs which are down here. So also for Sentinel-3, there's a replacement satellite which should come 18 months later, and the continuation of the JSNCS mission. So why, just very briefly, why is so important sea level change? So basically what we are seeing, which everybody knows, we have melting of the ice. And what is important to understand, that melting ice on the sea doesn't increase sea level change. So if you put an ice cube in a glass of water, it melts, you have the same amount of water in your glass. So very important. So it measures actually sea level change only is induced by melting ice on the continents. That's the first thing which we know, that the ice disappears. The second thing is that because of the warming of the atmosphere, we see a warming of the oceans. And if water gets warmer, it expands. So you can depict out of the sea level change two issues: the overall warming of the atmosphere and the melting of the ice sheet on the continents, which could give you an indication if there is climate change. And as I said at the beginning, climate change depiction only works if you have a long data series. So the US started in 1992, and the French stepped in, and you can see we see a constant change of roughly 3 millimeters per year. But this is a mean value. If you look in the news, everybody talks about sea level change, but it's not constant everywhere. So if you look at the distribution, there are a lot of questions about that. You can see areas where you have a strong rise of the sea level, and you have areas where there's no sea level change, which is basically in our area we don't see a change. But in the Pacific Ocean, in that area, we see huge changes, and you know all the discussions with some islands in these areas which are flooded. So there's still a lot of science questions to be answered, and which also has a connection to the gravity of the Earth, because the gravity of the Earth is not constant. So we have areas of the sea which are lower because of more gravity in that area, in the Earth's crust underneath. But these measurements are very important because it gives you really an indication what is happening, but you have to look what really is the implication of the sea level change in different areas. It's not constant over the Earth, so there's still a lot of science questions behind that. And as I said, we are preparing the operations of the Sentinel-3 mission, looking at ocean color, which is very important for fishery, and sea surface temperature. Basically. So we are doing, it also has land applications, but there was a political agreement with ESA that we are doing the ocean part and they are doing the land part out of the Sentinel-3 mission. And that is all for the first. So I think you should have a break, and me too. So, but if you have any questions, don't hesitate to ask. Okay. So I think in the program there's a coffee break now, and